that's our first definition of a sigma algebra. Let's recall, it contains the full set, it's stable under complements, it's stable under countably infinite unions and intersection, as we saw as a consequence here. Do sigma algebras exist? Can you name one example of a sigma algebra? To be sure, let's look at two examples of sigma algebras. So the first one that we will look is here. Let's look at this example. And let's look at the first example. Let's define F to be the collection of two sets, the empty set and the full set, nothing else. Extremely trivial. Is that a sigma algebra? Well, it contains the full set. That's the condition 1. Is it stable under complements? So if you take the complement of the full set, you get the empty set. If you get the complement of the empty set, you get the full set. So it's stable under complements. Rather trivially, it's also stable under countable unions. Okay, so this is the first example, sometimes called the trivial sigma algebra. Another example, another trivial example is the looking at the power set of omega. That is a collection of sets. It's the collection of all sets of omega. Is that a sigma algebra? Is it closed? Let's look at these axioms again, which are there on the top. Is this power set, is that a sigma algebra also? Well, of course, the power set contains the full set because it contains every set. Of course, it's stable under complements. Of course, it's stable under everything because it's the power set. So the power set is, of course, trivially stable under whatever you do. You cannot get out of the power set. Because the power set is stable under everything, it is also a sigma algebra on omega. Then we might ask, okay, are all families sigma algebras actually? The answer is no. So let's look at one example which is not a sigma algebra. Here is one example. Let's take the topology on the real line. So now F is the topology of the real line, the collection of all open sets on the real line. And the claim is that this is not a sigma algebra. Why is it not? Well, it contains the full set because the full set on the real line is open. It contains the empty set. But it's not stable for every countable intersection because we recall topologies are stable under finite intersections, but not countable. So if you look at this countable intersection, what happens? Let's see. What are we looking at here? We are looking here at this type of sets. So that's the open interval. If you look at this open interval on the real line, that's 0. And then we look at the open interval from minus 1 over n to 1 over n. And that's the open interval. That's an open set, so it's part of the topology. If we take the intersection of this for letting n go to infinity, so we take the intersection of this, then a smaller set, we intersect with even smaller set and even smaller set, so we take the intersection in the limit when we take the intersection of all of these 1 over n intervals, so we are left with 1 point only. That's the point 0 here. So this is the intersection, and this 1 point set is not an open set anymore. So this collection is not stable under countable intersections. And that's why this collection of all open subsets of the real line is not a sigma algebra. Okay, it's not a sigma algebra. So that's an example of a non-sigma algebra. Okay, maybe it's a time if you have questions about the definition. It's a really abstract definition. Let me open it again. And let me leave it there.